Well, hey everybody, thanks for coming this afternoon. My name is Jeff Sharkey, and I've been working on Android for about a year and a half outside of the Google team. And then recently, about 6 months ago, I joined Google, and I've been working on some cool stuff in the meantime. And today we're going to talk about battery life. So you guys got a whole bunch of really cool devices this morning. How many of you still have charge left on your device? You still have some battery life. Okay, so there's still some hands in the crowd. You might notice as you go through the day, you'll slowly watch that battery life go down further and further, and then the device will die. And that's something that today we're going to talk about. You as developers, as you're writing these applications, writing third-party applications, ways that you can make that battery last longer for your users that are out in the field, not just for yourselves. So just wanted to mention up front that as I go through the talk today, if you guys have any questions, if they come to you during the presentation, I'm using Google Moderator. So that you should have received links. There's links up on the screen right there. The have a sec, I don't know if that goes to the right one. But this link, code.google.com, that'll link you guys to the moderator, and then at the end of the talk. So there's a couple questions up there already, it looks like. And so I'll be switching back and forth between the mics and then moderator at the end of the session. So just a heads up, if you have questions, go ask. And also vote, because that'll bubble up the important questions to the top. All right, so battery life. Why does it matter? Why does it matter to the users that are out there? When we think of Android devices, they're mostly phones right now. And these phones, they might be on someone's nightstand, and then they take them out for the rest of an entire day. They leave in the morning, they unplug the device, and that device may not see power, it may not see a charge until that person gets home late that night. So during the course of the day, that battery needs to power the device. And the risk is that if the battery runs out during the day, the user can't use the device anymore. When the battery's gone, it truly is gone. It's a sad state of affairs. So the apps need to work together to be good citizens of the battery that's on the device. Because you're all running together. Your app is running alongside Gmail and Maps and a lot of these other apps on the device. So you need to work together with those apps to be good citizens. Today I'll be throwing around a bunch of different numbers, and I'll be using 2 units of measurement. They're actually SI units. The first type of measurement I'll be talking about is current, typically we think of this in amps, or milliamps is the unit I'll be using today. So if you think current is a way of saying how fast we're consuming the battery on the device, or the rate of consumption. So when you're doing a lot on the device, let's say you're watching a YouTube video, you'll be pulling a lot of milliamps on the device. The second number I'll be mentioning is milliamp hours, and that's a capacity. That's how much storage, how much battery life we actually store in the battery on the device when it is fully charged. So just some numbers for comparison. If we think of the HTC Dream or the G1 device that recently came out last October-ish, it had a battery of 1,150 milliamp hours. That was the capacity that it could hold. The device that you guys received today, the HTC Magic, has a slightly larger battery, about 1,350. And another device that was also recently announced in a press release, a Samsung device that runs Android, and its battery is about 1,500 milliamp hours. So something to realize between all 3 of these devices is that they roughly have the same battery capacity. They're all in the same class. It's roughly the same. And this is partially an industrial design problem. When you're building a phone, you want to build something that fits in someone's pocket. You don't want to build a device that they have to carry around a 12-volt battery with them. You want to have a device that fits nicely in their pocket. And so you only have so much room for a battery. And the way the technology is progressing right now, we're looking forward to having better battery life in the future, or better battery capacities. But for the moment, this is kind of what we have to deal with. Just to compare these capacities, something like a typical laptop that you might see, like an Asus EEE PC, its battery is about 3 or 4 times the size of what we're dealing with on these mobile devices. It's about 5,800 milliamp hours. And that's about the same as, if you know of a MacBook Pro, the battery in that's about 5,600 milliamp hours. So those are the types of numbers that we're dealing with. So then we can ask the question, we have that capacity. We have the 1,150 milliamp hours. Where does it all go through the course of a day as the user is doing different tasks? And so this is just an overview. If we start over on the left-hand side, if you have a device, it's booted, but the screen's turned off. It's sitting on the table completely idle, and it's in airplane mode. This means we've turned off all the radios in the device. It takes about 2 milliamp hours, or 2 milliamps of current that it's pulling just to sit there waiting for the user to wake it up, waiting for a user to wake it up and interact with it. If we add in one of the radio connections, let's say if we have an edge or a 3G connection just sitting on idle, it takes slightly a little bit more. It's about 5 milliamps that the device is pulling, just sitting there idle. On Wi-Fi, it costs a little bit more, about 12 milliamps of current that it's pulling. As soon as the user begins interacting with the device, this is where we see the jump. Just turning on the LCD on the device to display something to the user ends up taking 90 milliamps of battery. So anytime the screen is on, that's the amount of current that the screen is pulling. And as soon as we start adding in things like CPU, if you're doing 50% or 100% CPU, we can add, so 100% CPU, on top of the screen already being on, so this is the blue specific item, on top of the screen being turned on, 100% CPU ends up being 110 milliamps to run the CPU at full speed. Something, if you're looking at writing a game, running the game sensors, so the accelerometer on the device, this takes something like 80 milliamps of current that you're pulling. If you're trying to get a GPS fix using the GPS radio, that ends up taking another 80 or 85 milliamps that radio is pulling. And then finally, we get to the data on the device. When you have a data radio turned on and you're doing data transfer. So these numbers are full bore. We're transferring as much data as we possibly can. So we're stressing the radio out. We're doing lots of data transfer. So something like this, the 3G radio is actually pretty cheap in the device. It ends up costing about 150 milliamps just to run the 3G radio full bore so that you're transferring a lot of data. On an edge connection, it costs about 250 milliamps to run that radio at full speed. And then finally, Wi-Fi, which costs the most. It's about 275 milliamps to run that at full speed. So now that we know where it actually goes, let's compare those numbers. Let's take a moment and step back and think, do these numbers make sense? Do these match up with the real life battery statistics we're seeing in the field? So let's take a couple examples. Let's say you're watching a YouTube video. So this is something we're watching it on 3G. So we have the 3G radio spun up. We're doing a good amount of data transfer. We're transferring video. The CPU is doing a lot of work. It's decoding the video and then putting it on the screen for the user. And then they have the LCD on. So in total, watching a YouTube video is pulling about 340 milliamps of current. That's how much current it's using to show the video. And so we have those 2 units of measurement, or those two units, and we can divide it by the capacity in the device. And we can figure out how long the device should last, the expected life of the device. So something playing a YouTube video, that 1150 milliamp hours, the capacity in the battery, should last us about 3.5 hours of actual use of the person if they watched YouTube video continuously. Something a little more typical, browsing the 3G web. So it's a little bit cheaper. We're not doing as much data transfer. It's about 225 milliamps, or about 5 hours of battery life. So that's if the user is sitting there interacting with the device solid for 3 or 4 hours. A more typical use case is that they pull it out of their pocket maybe once or twice an hour. They're not interacting with it very much. Most of the time it's in their pocket. So a typical use case, we can think of the device being turned on about 10 minutes out of every hour. So we have the device turned on and doing activities for about 10 minutes, and the other 50 minutes of that hour, the device is in the person's pocket. It's asleep. It's using very little current. So if we average that out, it's about 42 milliamps on average over an hour. So if we do the computation, that battery life ends up that battery life in that case ends up being about 32 hours. And that's fairly typical. That's usually what we're seeing from people out in the field that are using G1 devices. They usually see a battery life. It lasts them about a day. So then let's take a look at the other end of the spectrum. Let's say we have a device that's just sitting there completely idle. The user isn't interacting with it at all. So the number that we measured earlier was 5 milliamps. That's the amount of current that it was pulling. If we do the math, the 1150 milliamp hours, the capacity of the battery, should last us about 9.5 days. And even further, if we have the device in an airplane mode, so all the radios are turned off, we're only pulling that 2 milliamps, it should last about 24 days. So then we can ask the question, where did all that battery life go? What's happening in between? What costs the most? What are we doing in the background that's using all of that battery, all of that capacity that the phone could use to last longer? So we can ask the question, what costs the most? And the first thing at the top of the list is waking up in the background. This is when the phone would otherwise be asleep in your pocket. You can have background tasks that wake up to go check the person's emails, say every 15 or 20 minutes, or every half hour. Or maybe an incoming email comes in and it needs to do some network activity. Things that the device wakes up to do in the background when it would otherwise be asleep end up costing a lot towards battery life. So let's take a typical example. Let's say you're writing an app that checks RSS feeds for new incoming posts. And let's check every 10 minutes. So this is just an example app, just for the sake of example. And when it wakes up in the background, it probably takes about 8 seconds to perform a full update. When you think of it, we're pulling up the radio stack, we're doing a DNS request, doing a network connection, pulling down the page, doing parsing on the device, and then it takes a few seconds for the device to settle back down and fall into a sleep mode again. So about 8 seconds of battery, and the battery usage during that period is about 350 milliamps. We don't have the screen on, but we're using a lot of data and a lot of CPU. So let's take a look at what this would cost during a given hour. So the idle cost, if the device was completely idle for that hour, it would cost us about 5 milliamp hours. That's the cost of the device just sitting there completely idle. But as soon as we add in this application that's waking up in the background, doing these seemingly innocent, just going out and checking an RSS feed, we do the math 6 times, so every 10 minutes, 6 times an hour, times the 8 seconds for each update, times the 350 milliamps. The amount of current that we're using there is about 4.6 milliamp hours. That's the amount that we're taking for this app to run. So just this small innocent app is actually cutting the user's battery life in half. And that's really something to realize. Apps like these are waking up and they can start using a lot of the user's battery without them even knowing. They think the device is turned off and in their pocket. And another thing to realize is that these apps waking up, it's not just your update that might happen. On the system, we have a notion of services that can only wake up, that can set alarms for themselves, that only wake up when the device is already awake. And so if you force the device awake, other services may piggyback on top of your waking up of the device. And so it actually, it compounds itself. Other apps jump on, and you can cascade a trigger a cascade of several of these updates all happening at the same time. So it might not just be your 8 seconds. If you wake up for your 8 seconds, you might end up being awake. You might end up forcing the phone awake for 15 or 20 seconds as other apps try to pile on and do their updates as well. So what else costs the most? Another thing that costs a lot is bulk data transfer. So we have phones with data connections, and as you can think of them transferring bulk data. We have people that are watching videos on YouTube. We have people that are generating content. They're taking pictures and videos, and they want to upload those. So we have heavy data traffic in both directions. And it ends up that bulk data transfer can actually cost a lot towards the life of a person's battery. So if we look at 3 different types of data connections that are available on the phone today, we have an edge connection, a 3G, and a Wi-Fi connection. And they all cost roughly about the same, about anywhere from 210 to 330 milliamps. Those numbers are slightly different because we're including CPU in those numbers from the numbers that I mentioned earlier. That's why they're slightly different. So they all cost roughly in the same ballpark to run those data connections. The key differentiator is that they can transfer at different rates. A 3G connection is a lot more efficient. It can transfer data a lot faster than an edge connection. Or even if you're familiar, there's a notion of a GPRS connection, which is even slower than edge. Whereas Wi-Fi can transfer stuff a lot faster. So let's take an example of a 6 megabyte song. You're writing a music store application for a person to go buy music, and you need to transfer 6 megabytes down to the phone. This is just bulk data transfer. We can do the math, and we can figure out how long it would take in each of those cases. To do that transfer on edge, it takes about 9 minutes. But to do it on Wi-Fi, which is a lot faster, it takes under a minute, about 46, 48 seconds. But then consider that we have to multiply that by how much the battery is being used over that time. So something like an edge transfer, the 9 minutes, ends up costing us 45 milliamp hours. That's how much battery we're using to do that data transfer. That same data transfer, that same 6 megabytes, would cost us an order of magnitude less if we did it over Wi-Fi, if we waited around to get a faster connection. It costs only less than 5 milliamp hours. So it's less than 10% of the original cost. Other things that end up costing a lot are moving between cells and networks. So as the phone, you can think of a phone as a person commutes with it at different locations. The phone radio ramps up to associate with new cells. So as I drove here this morning on a bus, my phone transferred between multiple cell towers as I went along the road. And as if you're riding Caltrain or something like that. So this is something we can't avoid. The radio chipset needs to wake up and be always associated so that the user can receive incoming texts and incoming phone calls. But on Android, we also wake up the system to possibly deal. Maybe your app, maybe an app on the system is interested when the connectivity changes. For example, if you have a photo that the user wanted to upload, you might want to check to see if the network connection goes up and down. So if the network connection comes back up, you may want to finish uploading your video. So the Android operating system allows us to wake up applications in the background using a notion of broadcast intents. I'll get into that a little bit later, but those actually cost a lot towards battery, especially when we're waking up those applications and they aren't going to do anything. If we wake it up to tell it network connectivity changed and it decides I don't need to do anything, it can end up costing a lot. Two other things in the end that end up costing a lot are textual data. So if we're receiving that RSS feed down as from XML, parsing that on the device can actually be really expensive. We're walking through the text data, we're trying to parse it. You can think of all the different data formats that you might have out there, XML or JSON, or even YAML, yet another markup language, which is its structure is based on spaces. So there's a lot of textual data that has to parse through. So parsing through text data that comes from the web can be really expensive, and I'll touch on that a little bit later, the differences between them. And finally, another thing that ends up costing a lot on the device is regular expressions, especially on Android. So the current virtual machine that we're using, the Dalvik VM, doesn't have just-in-time compiling, which is a luxury that a lot of people are used to from the desktop world. So in a desktop virtual machine, if we run into a regular expression, the desktop machine can actually compile a regular expression into really fast, tight code that runs very efficiently. But on a platform like Android, the current virtual machine that doesn't support just-in-time compiling, this can actually be pretty expensive. It can't optimize that just yet. So those are some things to be aware of. So then we can ask the question. So we know what the battery capacity that we're looking at. We know what things cost. And now we know what things actually cost a lot on the device. So how can we do better as we're developers, as we're out there writing apps? Today I'll be splitting this up into 3 separate sections. We're going to talk first about foreground applications, then we'll talk about, first we'll talk about networking, then foreground apps, and finally background apps. So first, networking. Check the network connection. So this comes back to you're about to do a set of bulk data transfers. You have that 6 megabyte song that the user wants to have downloaded. Something that you can do as a developer is you can check the current network connection that the user is on, that the device is on. So for example, if you know you need to download a lot of data, maybe you hold off on that transfer until the user comes into an area with 3G coverage, or they connect to a Wi-Fi network. So this is a quick code snippet example that Android makes it really easy to check to see what kind of network you're on. So I skipped past it. It was on the first slide here. There's a notion of a connectivity and a telephony manager that you can get references to if you have a context in Java. So with the connectivity manager, we can get an instance of the current network info, and that's what this info object is. And we can probe it. We can ask it about what type of network we're on that the user is currently on, what subtype of network. And then we can do some pretty quick logic to check to see if we should actually perform a transfer. So in this case, the first if block is checking to see if we're on a network connection of type Wi-Fi. And if that's the type that's currently enabled and we're connected to that network, return true. Let's actually perform the data transfer, because Wi-Fi is fast. It'll be cheap. Otherwise, if we're on a mobile network, let's check to see if we're on a 3G network. Another name for this is UMTS. There's several different 3G technologies, but this is the one that we have the constants for in the platform right now. And finally, one other thing that you can do as developers is you might be smart. You might check to see if the user's roaming. Roaming data can end up costing users a lot. And so if this is just something in the background and you're offering to download music for the user, this can end up costing a lot, especially not only time and battery-wise, but monetarily when they get their bill at the end of the month. So this is just one of those flags that we can check to see, is the network roaming? Some stuff that we can check to help our users in the end. So if that returns true, we can go ahead if we're actually connected to a 3G network and we're not roaming. Otherwise, we can return false. Some other choices here, too. Instead of just returning false, you might choose to involve the user in the process. So if the user takes a video and they want to upload it online, if you know that you're on an edge connection, you might actually do the math, do some quick math in the code to see, would I be able to transfer this without killing the device? Is there enough battery life left? And you might involve the user in the process and just tell them, transferring this file, transferring this raw data over edge is going to cost you a lot. You might actually lose your device because it would suck all of the battery life out of your device. And I may not even finish. And you might ask the user if they really want to go ahead with that. So instead of just blanketly canceling, you might involve them with that process and allow them to override it, because there's certain instances where they may really want photos to be uploaded right away. It also allows them to be aware of, so if they're on an edge connection and you inform them, they might know of a Wi-Fi hotspot down the street that they can go connect to. And so involving them in that process can really, you're helping them save battery. One other thing that we can check, so this is jumping back a slide. In the Settings app right now, Settings and Synchronization, there's a checkbox in there. And the user can the user can change the preference for using background data. The checkbox, right now, all of the Google services that are on the device look at that checkbox. And that's how they figure out what the user wants to do as far as data happening in the background on the device. And so if the user unchecks that box, the Google services will actually turn off. And they will only synchronize if the user goes into the app and forces it, or if they come back and turn on this checkbox. So this is something you as developers can also run in and check. If you have a connectivity manager object, you can check to see the state of that flag. And this is something that's new in Cupcake. And I'll be mentioning a couple features that are coming out that have come out in the Cupcake or the 1.5 SDK that recently came out. And I'll just indicate them with a little icon over there on the right. So that's just something to be aware of as we go through the rest of the presentation today. So we talked about bulk data transfer, involving the user in that process. One of the other things that can cost us a lot networking-wise is doing textual data, is transferring and parsing that text data. And as developers, we have a lot of different choices. A lot of us have a favorite data format that we like pushing stuff across the web. If you come from a RESTful approach of doing web services, maybe you're used to XML, or maybe you wrap your data in a JSON format. Or maybe you're used to other different formats, such as YAML, yet another markup language, or some of these other formats. Another popular protocol or another popular data format for passing stuff across the web is using a binary format. So if you're used to something called ASN1, it's a public standard for parsing or for packaging and parceling binary data across the web. Or something we've developed here, it's similar. It's another binary format. It's called protocol buffers. It's something that we've open sourced here at Google. And so it's a slightly more efficient way of packing data across the network. So you have all of these choices for the different protocols when communicating with the device. So we can ask the question, which one is the cheapest? What are the best choices? And so it boils down, we need to back up a second, and we need to ask ourselves the question, what type of parser are we actually going to use on the device? And most parsers fall into one of two categories. It's either a tree parser or an event or stream-based parser. So a tree parser is something, if you're used to in the desktop world of working with the DOM or the document object model in a browser, it parses the entire document into an in-memory tree that then you can go and interact with and pull data out of. But that tree can become really expensive on a mobile device. You're building the entire document into an in-memory structure, and maybe you're just going and pulling some of the data out of that tree, and then you end up having to dispose it. It becomes garbage that the system then has to collect. It becomes somewhat wasteful. So tree parsers can be pretty wasteful in these cases because they're generating a lot of garbage. On the flip side, an event or a stream-based parser allows you as a developer to become directly involved with the parsing process. So as the parser walks along a document, it actually has callbacks to your code, saying I found the beginning of a tag or the end of a tag, or maybe I found a section of text or a number or an XML attribute. And it can make these callbacks for you to handle in your code. It allows you to become directly involved with the parsing process. So the key takeaway there is to realize that event or stream-based parsers can be a lot more efficient memory-wise than tree parsers. So this slide is just a comparison on the device. Let's say we have a 6-item RSS feed that we want to pull down and parse from the web. And let's look at it from a number of different data formats. Let's choose 3. So we have XML or JSON or protocol buffers, which is a binary format. So in this case, we see on the left, those tree parsers in gray end up being pretty expensive. It takes a lot of time to actually parse and handle those documents. But then we see on the right-hand side, when we're using the event or stream-based parsers, it ends up being a lot cheaper. Especially, and then we can see the stair-step effect. XML is a little bit less efficient than JSON, and then protocol buffers, because it's a binary data format, ends up being pretty efficient. It ends up being the most efficient out of the ones that we compared here. So the key takeaway is use those stream parsers instead of the tree parsers. So this is something, if you're using XML pull parser on the device, that's one of the good parsers that you should be using. Sad to say, the JSON object and the JSON array libraries that ship with the platform, they're tree parsers right now. So it's something we'd like to find other libraries to integrate. So it's something to be aware of if you're parsing JSON data on the device. The ones that ship with the framework are tree parsers. So they're slightly less efficient. There's other libraries that you can use in their place. For example, the numbers that I did on the last slide, I used Jackson, which is another JSON library, which allows it to parse as a stream. So we have text formats, and then we also have these binary formats, like protocol buffers, or the ASN1. Another benefit to using the binary formats like that is that we can incorporate both text and binary data in the same request. And one place this is actually evident on the platform is in the Market client. If you're scrolling through a list of apps in Market, you might notice that all of a sudden, 4 or 5 icons of the apps that you're browsing through just appear all of a sudden. They don't slowly fill in. You'll see 5 at once. And the reason is we're using protocol buffers to actually bundle up multiple requests into a single request, and then we return the images in one bunch to the device. And this is really helpful on some mobile networks that can be laggy, where you have a lot of latency between yourself and the server. So instead of making an individual request for each of those assets, for each of those icons, we actually wrap that into a single request, requesting 4 or 5, and we get a larger response back that then we can parse. So something like a binary format like protocol buffers allows us to pack even multiple files into a single request coming back to the device. And that can really help you have fewer round trips and serve faster user experience to people that are using your apps. One other way that we can actually do a good job on the device as far as networking is using GZIP. If you're familiar with the desktop environment, some web servers support the notion of compressing the data before they send it to the browser. And almost all modern browsers automatically, when they see GZIP data coming from a website, will decompress it and show it to the user. And so many of you have actually used this in browsers today, possibly without realizing that it's happening under the hood. And GZIP is, so to back up a second, GZIP is compressing the data. The server compresses the data before it sends it across the network, and the device handles it. So in Android, the GZIP libraries that come with the platform are really efficient. And that's in part because they go directly to native code on the device. So if you're parsing a GZIP stream coming in, if you're decompressing it, it ends up being incredibly efficient, incredibly fast. So here's a quick example. If you're using something like the Apache HTTP client library, something a lot of us have used in our code, the first set of code should be, the first couple lines there should be pretty familiar. We're making a GET request out to a website and receiving something back. But in this case, if we know, for instance, that the web server we're talking to is going to be sending back compressed data, we only need to add one line of code, one extra step to decompress that data. We take the input stream that we're receiving from the site, and we just wrap it in a GZIP input stream. The system on the fly will decompress the data coming from the server, and so we can continue handling it. So we could pass that input stream, the decompressed one, into one of our data format parsers earlier. That takes an input stream into it. So GZIP on the platform goes directly to native code, and it's really cheap. So we can ask the question, how cheap is it? Should I consider using this? So just for the sake of an example, let's say we had a large RSS feed, say like 1,000 items. And this is what I did for this test. So if we're on a Wi-Fi connection, which is really fast, it doesn't make too much of a difference. We're looking here at the three bars. The raw data itself, so the raw XML. And then we compressed it using 2 levels of GZIP compression. Those are the 2 blue colors. And that's just the 2 levels. 1 is light compression, and 9 is the heaviest compression available. So on Wi-Fi, it doesn't make too much of a difference. But as soon as we start going over to a 3G or an edge connection, we can begin to see where the value of compressing the data comes in. So on a 3G network connection, just by compressing the data as it comes across the network, we end up cutting the transfer and parsing time, that total time, in half. And so it's not just the parsing time. Remember that this is battery time, because the radio is spun up that entire time. The CPU is spun up. It's waiting for data. It's parsing it. So this is the user's battery life. We've essentially, in terms of our application, we've doubled the user's battery life on 3G. And it's even better on Edge. Edge, to do this transfer, to transfer it across and parse it, ended up taking over 40 seconds. But that same data transferred across the network, if we GZIP, if we compress it, ends up taking under 10 seconds. So again, an order of magnitude. It's 10 times more expensive to do the raw data. Another thing to take away from this slide, you might wonder how expensive are the GZIP libraries on the device. And so we can see that with the Wi-Fi connection on the far right, even where it's not giving, we're seeing that adding GZIP doesn't cost us anything. It doesn't take us longer to parse the data, even when we have a really fast connection. So, and then one final thing to mention about GZIP is this is really helpful when you're working with text data. Text data can be really well compressed using GZIP. If you're doing binary transfers, if you're doing images or video, those items, because they're binary data, don't compress as well. So experiment with the data that you're using to see how well it compresses, to see if this would actually be an advantage. For most binary formats like the images and video, it won't actually offer you very much savings. Okay, so we talked about networking. Another thing that we can talk about is foreground applications that we're interacting with, that the user interacts with on the device. So if you're writing an app, there's a notion of Wakelocks that you can acquire to keep the device awake. Let's say, for example, you're writing a video application that you want the user to sit and watch videos in, something like YouTube. You can acquire a Wakelock, which forces the device to stay awake at least a certain level. There's multiple levels of Wakelocks in Android. You could request one of the lowest levels is just one that forces the CPU to stay on. So you acquire this lock that the system knows someone out there needs the CPU to be turned on. And then when you're finished, let's say you're parsing a document, you can release that Wakelock. And if the user isn't doing anything, releasing that Wakelock would allow the system to fall back asleep. And like I was saying, there's multiple levels of these Wakelocks. That's just one that would keep the CPU on. We can have other ones that, for example, keep the LCD on, which is very useful for something playing back video. We want the screen to stay on, so the user doesn't have to actively interact with the screen. Wakelocks can be really useful because they allow you as developers power in keeping the device awake. But on the flip side, they can actually be really expensive, especially if you forget to release them. Because even though we're working in a Java world, Wakelocks actually, the system acquires them and it doesn't garbage collect them. If you take out a Wakelock and you forget to release it, the system still thinks that you're out there having acquired it, and it will keep the system awake. So if your code crashes or if you forget to release the Wakelock, you might be responsible for keeping the device awake for a long period of time and possibly draining the user's battery. If you acquire a Wakelock and don't release it, the system will stay awake that entire time and possibly not allow it to fall asleep. So if you're worried about correctness, because I was mentioning there's these Wakelocks you have to acquire and release them. If you're worried about the correctness of proving that your code is correct, that you'll actually release them at the right time, you can do one. There's one of two approaches you can use. If you're writing UI from a user perspective, you can add one single tag into your UI, into any of the layouts, the Android layouts in XML, and that's Android keep screen on equal to true. Just using that, if you add that tag, you'll keep the screen on, and you don't have to worry about going and acquiring Wakelocks. You don't have to go touch them. The window manager in the device will actually acquire a Wakelock on your behalf when your application shows, and then whether you crash or the user switches to a different application, as soon as your activity goes away, the system will, on your behalf, release that Wakelock. So that can be one way of guaranteeing the correctness if you just need to keep the screen on. Another way is if you're acquiring these Wakelocks behind the scenes, say to keep the CPU awake while you're performing some parsing, you can actually set a limit. You can say, I'd like to acquire this Wakelock for at most 30 seconds, or for at most a minute. Or if you know the parsing, so if you know how long the worst case parsing is going to take, you can actually use that when you acquire the Wakelock. So if the system doesn't hear back from you, by the time that timeout elapses, the system will automatically release the Wakelock. And so if you know that you're just parsing an RSS feed and it shouldn't take any longer than 30 seconds, you can actually just set that as the timeout, and the system will release it on your behalf. So just in case there were any lagging issues in the code, any correctness issues, the system will release it on your behalf when the timeout passes. Another way we can help save battery from a UI perspective is recycling Java objects, especially complex ones. So yes, on Android, we have a garbage collector. So we can create objects and then they get garbage collected at a later date. But it's usually better in the long run if we just create less garbage. If we're running in a tight code loop, doing some text operations, building up a response to send back to a server on the other side, a response to send to the server. We can actually recycle buffers. If we recycle objects inside of that tight loop, we end up creating less garbage overall. And there's a couple places that this shows up in the system. One is XML Pull Parser Factory, and this is just an example. It borrows from the factory design principle, and it also keeps some generic state for all XML pull parsers that you might acquire. And so using the poll parser factory allows you to get an instance of a poll parser as you need it with very low overhead. It takes care of recycling some of those objects. The same with bitmap factory on the device. If you're acquiring bitmaps for various things, using bitmap factory internally, it keeps a pool of bitmap objects that it's prepared to send to you, almost pre-warmed, ready to give to you. And then when you're done, you can release them back into the pool to be recycled. So some of these things can really help you recycle objects in your code. Two other places that this can show up, if you do find yourselves having to use regular expressions, in Java, regular expression, we compile it into a pattern, an instance of the pattern class. And with that pattern class, we can get a matcher for a given string. And one mistake that I've made in my code before is that I've acquired a new matcher object every single time for every single string that I want to match that regular expression against. And something I need to remind myself of is that I can actually recycle that matcher object. I can call a method on it called reset and pass it a new string. So this can be a lot more efficient. If you're writing a tight code loop where you're parsing multiple strings, you can recycle those matcher objects. Also, in the case if you're building strings for a UI, you might end up using something called string builder. So remember in Java that strings are immutable, and every time we use the plus operator to concatenate strings together, we're actually acquiring a new string and throwing away the two old ones. So something like string builder actually acquires a byte buffer in the background, inside of the object, and you can append things very cheaply to it. And you can also recycle those string builder objects. You call setLength0, and it actually just erases everything that's in the string builder, allowing you to build a brand new string, and you don't have to reallocate the buffer that's underneath. Some of these recycling issues, you might find yourselves you can create a static object that you might borrow between multiple methods. And sometimes that can introduce synchronization issues or correctness if two different threads are borrowing the same object in code. And this actually this can be solved in Android because we're using a single UI thread model. If it's UI driven, for example, if we're recycling a string builder, instead of allocating, let's say you were writing a list view, and there's a bind view method where we're actually setting the text for the item in the list view. Instead of allocating a string builder inside of each call of the method, we can actually share an object, a static object, inside of something like that list adapter. So on Android, because it's a single UI thread-based model, we know that code is only going to ever be called, that method is only going to be called from the UI thread. And we can guarantee that the synchronization issues are solved in those cases. So it's something to handle a case-by-case basis, but just to remember that Android is a single UI thread. It can help solve some synchronization problems. And I was mentioning list view. List view actually uses a lot of recycling strategies. If you're interested in digging more, Roman Guy's talk later, I believe it's tomorrow, he'll be diving into list view a lot more on some of the recycling strategies that are used in list view. So other ways with foreground apps that we can end up saving battery. A lot of people write geolocation apps, apps that need to know about the user's location. So something you might want to consider is using the coarse network location. So on Android, we provide two different providers of the network of the location of the device. One is a network provider, and one is GPS that the device also happens to have. And it ends up that using the network provider is a lot cheaper. So network provider, this is something that Vic was mentioning in his keynote earlier today, is that we might use nearby cell towers and Wi-Fi access points to triangulate where the user is. That can actually be really cheap on the device. We're just looking at some sensors, pulling in the cell towers that we see, and asking a server to triangulate on our behalf. And that can actually be a lot cheaper than doing GPS. That's because GPS fixes, getting a fix from satellites, the time to fix, the time it takes us to get a fix of our location from the GPS satellites, it varies wildly. It can be any length of time. If you're out in the middle of an open field, the fix may only take a few seconds. But let's say you're in an indoor environment like this, here in this conference here today. You might even your device may look for a GPS satellites, and it may never find them. We may keep the GPS radio awake that entire time and never actually get a fix. There's a risk of us not actually getting the latitude, longitude. So it's something to be aware of. If you're interested in just rough location, if the accuracy that you're interested in is just within a couple kilometers of where the user is, network location can be a lot cheaper. In fact, and so the numbers here that we're looking at, an average GPS fix might take about 25 seconds. And then we multiply that times the actual battery that's used during that time. It ends up costing about 1 milliamp hour on average to get a GPS fix. whereas getting a network fix is an order of magnitude cheaper. We're just doing a quick, simple network query based on information, the cell towers that we already know about. And also you notice the cupcake there. Something that in 1.5 we're actually using assisted GPS. So when we have a GPS and we first bring it up on the network, there's something known as a cold start. So if the user hasn't used GPS in a while, the device has to sit and listen for the satellites to send down an almanac or a set of information describing the movement of the satellites. And that can happen a lot faster if you use something called AGPS or assisted GPS, where instead of listening for that almanac data over a low bit rate, the satellites are transmitting it at all times, but at a very low bit rate. Instead of waiting a couple minutes to collect that almanac information, AGPS goes to the network. It assumes you have a network connection. It can go request that almanac information, which allows fixes to happen a lot faster. So that's something that shipped in 1.5. Some final things to mention about foreground apps is that floating point math is expensive on the device. The current devices that have shipped don't have floating point units in their CPUs, and so doing floating point math is expensive. If you worked with map activity or map view on the device, you may have noticed something called geopoint. And so it's just like a latitude, longitude, which are decimal numbers, except it's multiplied by 10 to the 6. We just shift it over the decimal place. So we can treat these as integers, which ends up being a lot cheaper when we're working on the device. And also, if you end up writing your own views, you may need to worry about scaling to different densities of devices. A device may have a higher density screen. And so you can actually, and that density is expressed in a float. So if you're writing your own views, you can pre-cache that. If you pre-multiply that density that's coming in, you can often cache the value and end up saving time in the long run. And one final mention, if you're looking at using the accelerometer or game sensors, there's 4 different rates, 4 different polling rates that you can use. Normal, UI, game, and fastest. And there's various, they each have their own cost associated with them. Usually when you're using the accelerometer, the user is playing a game, so you need it anyway, but it's just something to be aware of, that this is the cost that's added on. So we talked about network, and we talked about foreground apps. And finally, I'd like to take some time to talk about background applications on the phone and how they can do better managing battery life. So first of all, let's back up and talk about services in general. If you come from a Unix or a Windows background, when we think of a service, we think of something we start in the background and it continues to run, almost like a daemon. So it's waiting for requests to come in. It's running at all times. And that works really well in the desktop world. But in the mobile world, each of those processes running, each of those services, has an overhead associated with it. So say, for example, some of the devices that first came out, say the HTC Dream device that came out. When the system finally boots, so we think we have an amount of RAM on the system, and the system boots. We have an amount of RAM that's reserved for the kernel, and then we have some RAM that's reserved for the Android framework. And when the device finally finishes booting, we have roughly about 30 to 40 megabytes of actual RAM that foreground applications and background apps on the device can make use of. And something to be aware of, that each process on the device, even if you're running a lightweight service, takes somewhere around 2 megabytes of overhead just to start that application. And that's just the foundation of starting your app. If you're doing other things on top of that, that's even more RAM that you end up using. So, and then finally, if you have a service that's running in the background constantly, the system will actually kill you. If the user is doing some foreground task, say like using the browser, and the browser needs more memory, it will go through and kill off some of these background services. And it will try restarting you at a later time so you can continue whatever work you were doing in the background. But again, it's that overhead of having to kill you and then come back and restart you can really add up over time. Okay, so we asked the question, if we can't have the service running at all times in the background, if we can't use a daemon model that works really well on the desktop, how should we write services? And there's 2 primary methods that we can use. One is if you have a point in the future, have a time in the future that you know you need to wake up, say you're performing an RSS feed update every 15 or 15 minutes or half an hour, you can set an alarm for the system to wake you up at that point in the future. And another method is using a broadcast receiver. So it allows you to be event-driven. So if the user moves between network connections, for example, if they're on an edge network and they transfer to a 3G, if they all of a sudden get a 3G connection, broadcast intents, the system sends a broadcast intents that anyone interested can pick up on and handle. So those are just 2, I'll jump into those more in detail, but those are the two of the methods that you should use as writing services. And a final note is, once you handle, if your service is woken up and you handle one of these events, make sure to call stop self if you're writing the service, which tells the system that you're finished with whatever work you were doing, and the system can kill your process. It's free to kill your process. So remember to stop self whenever you're done processing data. So first, let's jump into those two types, using Alarm Manager, and then later we'll talk about the broadcast intents. So first, Alarm Manager. If you have a point in time in the future that you know you'd like to wake up, you can have the system wake you up to perform that action. And so it allows you to set a specific time, using a notion of an RTC, or a real-time clock. So if you're familiar with the concept of Unix time, on Android, the RTC is the number of seconds, the number of milliseconds since the epoch, back in 1970. So you can specify an exact time that you'd like the system to wake you up, to perform some action in the future. You can also specify, you can add in a flag. So here at the bottom, we're using the alarmmanager.rtc flag. There's other flags that we can use. We can use RTC_wakeup. And what that does is that forces the device awake. So if we get to that point in time, and we absolutely need the device to wake up, let's say, for example, we're writing an alarm clock. We need to wake up and tell the user to get out of bed. We want to wake the device up if it's sleeping. So we should use the wake up flag. Otherwise, if we don't use that, the service will only start at that point in the future if the system is already awake, if it's awake handling other things on behalf of the user. So another thing we introduced in Cupcake, we have the notion of repeating alarms. We can set an alarm, say you wanted to update your RSS feed, or you have a Twitter feed that you want to update every 15 minutes or so. Currently, right now, the old approach in the 1.1 SDK, you set a repeating alarm and you set an interval. You set 15 minutes. And the system would actually set those alarms. So here on the left-hand side, this is an example of what it used to look like. Let's say you had a Twitter and a news app and a mail application that all wanted to wake up, say, every half hour in this case. And so we would run into the worst-case circumstance where the Twitter application would wake up, and then the system would fall back asleep, go into an idle state for about 10 minutes. And then the news application would wake the device up and do an update, and then fall back asleep for another 10 minutes. And then the mail application. You can see how that's a worst case of all of these being spread out across time, and the overhead associated with waking up the system each time to go do network activity and falling back asleep. There's all that extra overhead. So something we introduced in 1.5 is the notion, Alarm Manager has a new method called set inexact repeating, which allows you as a developer, if you're willing to be flexible with the time interval that you're woken up with, if you're saying, I'm okay with being woken up every 30 minutes-ish, if you're okay being adjusted around, the system will offer to bin you together. It will bin you together with anyone else that's interested in updating at the same interval. So in this case, those three applications, if they use set inexact repeating, the system would group them all together. It would look and compare and group everyone together and to do one single update. We'd wake up the device, perform all three updates, and then fall asleep for an entire half hour until the next set of updates happened. So that's something to be aware of in the 1.5 SDK if you're looking to do some things in the background. Okay, so that covers Alarm Manager. One of the other methods that you can wake up from a service, or wake your service up, is using the notion of broadcast intents. So the system, here's just a couple examples that can be really useful for developers. For example, if the time zone changed, if you're writing an application that wakes the person up, maybe you're interested in that, or if you have a calendar application. The second one is probably one of the most important, Connectivity Manager. Something happened with the network connection. We changed. We were on Edge before, now we're connected to Wi-Fi. Or maybe we lost network connection altogether. Or maybe we didn't have network connection and now we're connected to Wi-Fi. That broadcast intent, that Connectivity Manager .connectivity action, is sent out by the system every time the network state changes. So that's something you can listen for. The same if let's say you're holding a cache on the device and you're interested when the device storage is low. Maybe you have a cache that you can clean out to help make room for the user. You can listen for that broadcast. Or if you're doing some background tasks, you can listen for the battery low broadcast. So if the system will send this out at the same time that it shows the notification to the user that they have 15% of their battery left. So if you're doing some background tasks, you might fall asleep during this period and wake yourself up maybe a day later when you might have more battery. So you could use that to cancel some background tasks. So this is one quick code snippet about how you'd register for these. So just like we have an activity or a service definition in our Android manifest, we define a receiver and then an intent filter that matches any of those intents that we're interested in. So part of the issue is that connectivity manager actually happens a lot on the device. As I was mentioning, if the user is moving between Edge and Wi-Fi, every single one of those actions will wake up your service because you've told the system that you're interested in that update. It will wake you up every time. And the risk is that, let's say you're writing an application that uploads video, say to YouTube, on behalf of the user. If you register for this broadcast, the risk is that most of the time, the user isn't going to have a video waiting in the queue to upload. They might not have anything to do. So your process, your service that you're writing, will be woken up for every one of these connectivity change events, even when you don't have anything to do. And that can cause a lot of overhead. So one way to solve that is actually enabling and disabling those manifest elements. So we define the manifest element using that receiver tag. We can programmatically, at runtime, enable and disable it. So we can get those broadcast intents when we need them, when we need to know about them, and we can turn them off when we know we wouldn't be doing anything. So something like this is a code example at the top here. We're starting with enabled equal to false. We're not going to receive any of those broadcast actions. Then in the code later on, let's say the user has a video that they're ready to upload. In that code, we can actually grab a copy of the package manager and find the component name for our broadcast receiver. And we can dynamically enable it so that we start receiving those broadcast intents. So that as we're uploading the video, we watch to see as the user changes between Wi-Fi to Edge to 3G so that we can handle it correctly. And then the same code works in the inverse case. Once we've finished uploading everything on behalf of the user, we can go and disable this manifest element again because we don't have anything left in our upload queue. And we would just be using system resources when we don't have anything to upload. So this can really help us be more efficient. Another thing that we can do is actually we can check the battery state. And this is a little bit of a tricky code example. You can check to see the battery percentage that's left. The system sends out a broadcast intent, a sticky broadcast that sticks around that you can catch that has the current battery level. Say it'd be like 40% or 45%. And so you might be interested in getting that exact number so that you could do some calculations. So if the user's on Edge and they have more than 60% battery, maybe it's okay and you want to go ahead with that. So this is a quick code snippet that would explain how to go grab that broadcast. It's a little bit hard to explain, and I know we're running a little short on time. So we'll skip it for now. Okay, so we talked about how we as developers can save battery, both in terms of network, foreground apps, and background apps. So now let's talk about what's beyond 1.5, beyond Cupcake. What's coming next? So here I'd like to show an example. This is actually in spare parts on Cupcake. It's not on your phones that you got today because those are user builds. If you go home, you should be able to reflash your phones with an engineering build, which will give you root, and it will start collecting battery statistics. So this is an example of what that screen looks like. The system is actually keeping track in 1.5 now of each of the applications and how much they're doing with respect to various pieces on the system. In this case, we're looking at how much network activity each of the apps, and we're tabulating, we're keeping these statistics. So it's something that's not exposed just yet, but in future versions down the road, this is something we'd like to expose to end users. So they know, for instance, that my device's battery doesn't last very long. What can I do about it? So this will be an answer. This will be a place that they can go and actually check to see who on their phone, which applications are using battery. So this is something that you guys can use as you're working and debugging your applications, but it's also motivation. It's also motivation to be aware that users will be watching in the future, and they'll be able to see which apps are using battery, and they'll actually uninstall you, and then you won't be around. So one thing to keep in mind, if you're writing apps, give your users flexibility. Say, for example, you're writing a stock ticker application. Some of your users may only be interested in getting updates once or twice a day, but other users may be really interested and want updates every 5 minutes. So giving your users flexibility on how much they want to update will make them less likely to uninstall you because they have a choice. They have some control over the amount of battery that your application is using if they can change preferences inside of your app. Okay, so some overall takeaways about everything we talked about today. First of all, use an efficient data parser. Use one of those event or poll-based parsers instead of a tree parser. Also use GZIP to compress text data if you're sending a lot of textual data to the phone so that you can save network and CPU resources. Services that sleep or poll are bad. So don't use the daemon approach from the desktop. Instead, be event-driven. Set alarms for yourself to wake up in the future and respond to broadcast intents. Also, disable those manifest elements. If you're interested in those broadcasts, disable them when you wouldn't do anything. If the system is just going to wake you up to look and decide that you're going to fall back asleep again, disable it. Disable those manifest elements in those cases. Also, wake up along with everyone else. That's the set inexact alarms, repeating alarms. Also, wait for better network or battery before you do bulk transfers, and possibly involve the user in that process so that they know they can go find Wi-Fi somewhere if it's going to affect their battery life. And finally, give choices to the user about the background behavior of your apps. It'll allow them to be much more. You'll be much more friendly towards users because they have choices. They have a choice now between how much battery you're using in the background. So with that, that's about all I had to talk about battery life. It looks like we have just over 5-6 minutes left for questions. So I'm going to switch over to Google Moderator, and then also feel free to come up to the microphones to ask any of your questions. And then we'll alternate back and forth between everything. Okay, so first question to moderator. Someone asked, what happened to the Google I/O apps? I can't find it on Market. So over the weekend, a couple of friends and I wrote an application for the schedule for the conference, and you can find it on Market. You can only get it on Cupcake devices, and if you go to Market and just search for I/O as a single word, you should be able to find it. Let's take a live question over here on the left.
Yeah, real quick. You didn't mention the overhead involved with UDP transmissions. How does that compare?
Okay, that's a good question. So, right, there's a little more overhead with TCP connections because we need to build up the entire transaction. There's a SYN-ACK process that happens between both ends, so there's more latency involved. So there's a little more setup time there. I would expect that UDP is it's cheaper, but when you think about it, the devices are running on mobile networks that are definitely not as reliable, and so UDP doesn't give you any guarantees that your message actually got to the other end. So in most cases, you do want to use TCP just because you'll have that guarantee that it made it across the mobile network, which might be flaky. So UDP might offer you some savings, but I'd say in the long run, you're probably going to want to go with TCP. Let's take a question over on the right.
Me?
Yeah.
What about screen brightness? How does that affect the battery?
So I took a peek at that. So there's the 0% brightness on the screen. You can turn it all the way down, so it's very, very dim. It ended up still taking quite a bit of battery. I think it was about 70 milliamps at the lowest brightness. And part of that was because we're actually driving the entire LCD. We have that refresh rate of up to 60 hertz that we're pushing pixels. And so there was a lot of cost with that. And it was a little higher. I think it was about 100, 110 if we had it at 100% brightness. So roughly in that ballpark. So the sweet spot that the device, someone asked the question in the crowd, what is the sweet spot for the display brightness? And the default one that ships with the device that most users don't change it from, that's the number that I mentioned there, which is about 90 milliamps that it ends up costing. That's right in the middle of the road. Let's take a couple questions from the moderator. Someone asked, are there any battery profiling tools out there? And the short answer is, sadly, no, there isn't. However, there's a direct correlation between how much processing, how much CPU you're using, and the impact on battery life. So if you're using tools, if you're using TraceView, which is one of the tools that's distributed with the SDK, to look at the amount of time that your code is running, it allows you to do method-level tracing to see how many times methods are called and how much time overall your app is taking for certain operations. If you're using TraceView, that's a good indicator of how much battery you're using on the other side. So sad to say there aren't any direct profiling tools, kind of because measuring milliamps is somewhat of an electronic black art. You can't do it in software. You actually need specific hardware to directly measure it. Take one more question from moderator. How can you customize the power management features of Android to enable more power modes? So this is actually the base Android system. Doesn't come with very much profile management, but this is a place we've actually seen in the market. Several apps have stepped up to the challenge and written apps that help the user manage their battery life. So for example, Locale was one of the winners of the first ADC, which allows you to change your network preferences to turn on Wi-Fi when it sees that you're getting near your home. And to turn Bluetooth off when you start getting on the train because you want to listen to music on your Bluetooth headset. So there's apps out there. I don't think, as of right now, I don't think there's any plans of including that in the platform. I think it's a niche that third-party apps have filled very well. Let's take a question from the right.
I actually have a question quite long. So one is, can you go back to the slides of the sensor, the gaming side? So. And how you calculate, that's how you calculate the 10 millions. Actually, accelerometer itself only consumes less than 0.5 millions. and what is like an orientation?
Right. Okay, so that's a good question. He's asking, the actual sensor in the device is very little power. The accelerometer in the device, the hardware, the piece of hardware that measures the accelerometer, that device uses very little power, only a couple milliamps. The overhead that we're seeing here, the cost between these polling rates, is because the device is shipping that information, those details, the accelerometer, the actual measurements, up into Java code. And that's where we start to see the overhead. We have to marshal that into the Java environment. And that's where we see the overhead. That's where we start seeing this battery life. So these battery measurements aren't strictly the cost of running the accelerometer. They're the overhead of actually having to pass that information back up into the Java world. So
yeah, along that, so how you think we can reduce that by like interrupt driven by have the interrupt for orientation detection, then you can reduce the traffic.
Okay, so this
because I think the sensor manager in the Android do not take interrupt.
Okay, so right now the sensor manager is just available from Java code. So we're stuck with this overhead right now. With some of the other stuff that Dan Morrow was covering this morning, talking about writing native code, I don't know if there's efforts to have Sensor Manager available in native code, but that would actually help save some of this overhead. If you're writing C++ code that can look directly at the sensor values, you can really help save some battery. You don't have the overhead of going all the way up to Java. Again, it's something I'm not aware of that people are working on right now, but it's definitely would help in the long run for game developers. Let's take a couple more questions from moderator, because these are the ones that you guys have voted up over the course of the talk. Okay, someone asked the question, what is the rule of thumb for employing caching of data to avoid repeated data transmissions and consequently draining the battery? I have about 10 seconds left, so I'll quickly try to answer this question. So on the device, probably the best place to use to store a data cache is on the SD card. When you store it in the internal directory, internal structure for your app, you're actually counting against the space that the user could be installing other apps into. And so it's probably best to use the SD card. And you can also check the SD card state using the environment object in Java. With that, I think we're about a half a minute past time. I'd be happy to talk with any of you guys. If you have questions afterwards, come up and talk. And thanks for your time.